Hi everyone. Today we're going to be talking about electric fields. Electric fields are a way of thinking about electric charges that helps us to understand how they will affect other charges. We can see here a pair of parallel plates. Now the way parallel plates works is that one of the plates will be set up with a positive charge and the other with a negative charge, and this will create an electric field. So what exactly is an electric field? Well, in physics, whenever an object attracts another object at a distance without touching it, then we say that the object is surrounded by a field. This is true of a number of different fields in physics. We can talk about magnetic fields, which is the area where something can be attracted by a magnet. We can talk about gravitational fields, where something will be attracted by gravity. Or we can talk about electric fields, where things can be attracted by electric charges. So the Earth will attract us with gravity, so we say it has a gravitational field. The gravitational field happens to look something like this diagram. Charged particles are said to have an electric field, and there are some charged particles which will have an electric field that looks like this as well. Now, electric fields have both magnitude and direction, which means they're not a scalar. The quantities are determined by the force that a positive charge would experience inside the field. So we can call this a vector field. If we put a positive charge inside this electric field that we can see in the diagram, it'll be attracted toward the negatively charged plate. That means that the direction of the negative field is downwards towards that plate. We draw field lines to represent the field, which we can see in this diagram over here. They're just straight lines with arrows on them. Now, a positive charge repels positive charges. That means that the field lines near a positive charge point away from the charge. We can see that in this diagram over here. We have a positive charge in the center, and the electric field lines point away from it. If we put a positive charge near the first one, it will move in the direction indicated by the field lines. Now, a negative charge does quite the opposite. It attracts positive charges, which means that if ever we look at the field lines around a negative charge, they will always be pointing towards that charge, right? Now, stronger fields are represented by closer together field lines. And we can see from these diagrams over here that the closer we get to the particle, the closer together the field lines get, which means that the electric field is getting stronger close to the particle. Algebraically, we represent electric fields with a capital E. Don't confuse it with energy, which uses the same symbol. Now, their strength is measured in newtons per coulomb. We'll learn why in a little while. The thing is, we don't have to use newtons per coulomb. We can also measure it in volts per meter. It turns out that if you go into the definition of a volt and the definition of a coulomb, then these units, volts per meter and newtons per coulomb, will be exactly equivalent. No matter which way you look at it, 1 newton per coulomb is exactly the same thing as 1 volt per meter, simply because of how newtons, coulombs, volts, and meters are defined. So the units are exactly equivalent, and we can use them interchangeably. Now, what about the direction of the force? Well, we've touched on this before. It turns out that we can use an equation, a very simple one, to figure out how much force acts on a particle. That's in an electric field. Force equals Q times E. So Q is the number of coulombs on the electric charge, and E is the strength of the electric field in newtons per coulomb. So if we take newtons per coulomb and multiply it by a measure of coulombs, we end up with newtons. Now, if Q is positive, that means the direction of the force will be the same as the direction of the field. Remember that force and field are both vector quantities. So, if we have a positive charge, like in the top of the diagram, and the field points to the right, then the force will also point to the right. If, on the other hand, we have a negative charge, like in the bottom of the diagram, the direction of the force, F, will be negative the direction of the field. And so if the electric field points right, the force on the negative charge will point left. So that's the end of the theory. We've learned a bit about electric fields in this section. Let's go on to some questions, shall we?